Hello everyone, I'm Eugenio Marinelli and I will present our work towards migration-free just-in-case data archival for future cloud data lake using synthetic DNA. Over the past few years, driven by analytics and AI, we have witnessed a rapid growth in popularity of cloud data lakes. Naturally, an enormous amount of effort is being made in advancing various aspects of data management, mainly related to just-in-time data analytics, focusing on the first two layers of the tiered storage hierarchy. However, as data keep accumulating, it is becoming increasingly more important to focus on yet another task that has historically received much less attention, the one related to just-in-case data archival. In fact, enterprises need to archive data in order to meet just-in-case safety, legal, and regulatory compliance requirements. Today, over 80% of data stored is archival in nature, and archival data is the fastest growing data segment. For this reason, as enterprises migrate to the cloud, cloud data lake will be soon, if not already, in need of archival storage technologies that can provide high-density, low-cost storage for long periods without degradation. Unfortunately, current media technologies are unable to meet these requirements as they have fundamental limitations. First, all media technologies suffer from decay due to a limited lifetime, up to 10 years for magnetic tapes. Second, current media technologies tightly couple the storage medium with the technology to read data off the medium. This coupling leads to media obsolescence, with data stored in an older medium no longer being readable by newer readers. For instance, LTO drives are backwards compatible only with two tape generation for read and one generation for write. These hardware issues lead to expensive, cumbersome, periodic remastering where data is migrated from an older generation of archival media to a newer one. Researchers started to investigate alternative storage media for long-term archival. A valid candidate is synthetic DNA. The reason is that synthetic DNA potentially overcome all limitations affecting the traditional magnetic media. First, it is extremely dense, up to 7 orders of magnitude higher than the best expectation for magnetic tape. Second, it will never become obsolete as technology because the technology to read DNA is independent from the medium itself. Finally, it is very durable, meaning it can last thousands of years even in non-optimal environmental conditions, as evidenced by the fact that scientists were able to extract and read DNA from the remains of a mammoth that are thousands of years old. For this reason, it doesn't require periodical data migration, which is not the case with the traditional storage media. In our vision, Cloud Data Lake can achieve a migration-free data archival using this novel, obsolescence-free biological medium that is synthetic DNA. To store data on DNA, we need first to encode the binary data as a sequence of 4 nucleotides, the building block of DNA represented by their initial letter A, C, G, and T. Then these sequences, also called oligos, are manufactured as actual DNA strands by a process called synthesis. Reading data back involves a chemical process called sequencing, which generates copies of our original oligos. However, these copies are not exact duplicates of the original oligos because they can have errors such as insertion, deletion, and substitution. The reads are then fed to a consensus algorithm that try to infer, despite this error, the original oligos. Finally, the inferred oligos are decoded back into bits. So far, all the state-of-the-art solutions implemented in this pipeline have in common two characteristics. They use nucleotides as building block, meaning the oligos is built one nucleotide at a time. Blocks of bits are then mapped across multiple full oligos. For this reason, they need to separate consensus calling from decoding, because we first need to recover all the oligos entirely before being able to retrieve these bits. However, consensus caller is inaccurate, so decoding needs to have additional parity bits to deal with those errors. On the other hand, additional parity bits increase the cost of storing data on DNA. The key observation for our work is that the separation of consensus calling from decoding in every state-of-the-art pipeline leaves some margin for optimization. Therefore, can we integrate consensus calling and decoding to reduce disparity information? To answer this question, in this work, we came out with a different version of this pipeline that we called OligoArchive DSM. It is an end-to-end DNA storage system that integrates consensus calling and decoding in one stage. This is possible because we exploit a motif-based encoding decoding technique in which, instead of using a single nucleotide as building block, it is used a fixed library of shorter oligos called motifs. Then these motifs are organized following a columnar layout in the oligos dataset. To understand better the columnar layout, let's compare it with the state-of-the-art layout. So figure A and B are in common to both state-of-the-art pipeline, OligoArchive DSM pipeline. Bits are grouped in smaller blocks. Each block is extended with index and parity information, but then the state-of-the-art pipeline scans sequentially the bits and start building the oligos one nucleotide at a time by making one full oligos after the other. On the other hand, OligoArchive DSM adopts a different strategy. We see the oligos dataset as a table, whose rows are the oligos and the columns the motifs. Then OligoArchive DSM encodes every data block in a different column. To understand the benefit of the new data layout, let's walk through this small example. Every block of our input data is encoded as a different column of motifs. As a result, we have a set of oligos, each one made by different motifs of length 4. After sequencing these DNA strands and clustering the resulting dataset of reads, we get a set of clusters. Remember that the reads are copies of the oligos, and for sake of simplicity, in this example, we assume that we have only one read per cluster. Notice that sequencing introduces errors, so the reads are not exactly copies of the oligos. For example, the blue motif in the read 1 has a deletion of the second nucleotide. Therefore, it will end up misaligning all the motifs downstream. Despite it seems obvious from this example, in a real experiment, it is impossible to detect insertion and deletion at this stage. So we go ahead. For each cluster, we apply consensus only on the first column. As a result, we get a column of inferred motifs and we decode it. As expected, some of the bits will be wrong, as some of the motifs are wrong. Fortunately, we add some parity information during encoding, so we can recover back our block of bits. The block is ready to be part of the final output, but that's not the end of this process. Here, the key point of OligoArchive DSM. We re-encode once more the corrected data block in order to get a corrected version of the first column of motifs. At this point, we can align the correct motifs against the wrong reads in the cluster, and we can identify insertion and deletion and adjust accordingly the starting position of the next column of motifs. In this way, we stop insertion and deletion to propagate until the end of the oligos. Notice that without the motif structure, the columnar layout, and the realignment, it is impossible to identify and fix insertion and deletion in the reads. The process is then repeated for the other columns. To prove that this process works, we conducted a wet lab experiment in which we encoded 1 megabyte of a compressed relational database using 44,000 oligos. We sequenced the DNA strands, generating 43 million reads, in which every oligos is repeated about 951 times. This factor is called coverage. We tested the decoding using the full dataset, and then we reduced the coverage by subsampling from the reads dataset. As a result, we are able to decode our data up to a minimum coverage of 4 times. This experiment shows that OligoArchive DSM allows to reduce significantly the read cost compared to the state of the art. To conclude, the current tape-driven migration-based archival suffers from fundamental limitation, which makes cost-efficient data archival infeasible. Synthetic DNA can be used as obsolescence-free storage medium. In this work, we implemented OligoArchive DSM, an end-to-end pipeline for data archival that significantly reduce read and write cost compared to the state of the art. There are several other research directions that are relevant to the data management community. One of the open questions concerns metadata archival. In order to recover the data stored in DNA, the oligoarchive DSM decoder needs additional information, additional metadata, such as LDPC matrices, in order to retrieve correctly the bits stored in nucleotides. As the decoder will be run in the future, it will be necessary to save somewhere this metadata. In ongoing work, we are developing a tiered solution where data will be stored on DNA with oligoarchive DSM and metadata will be stored on analog media. The two can then be stored together as a unit passively, eliminating completely the need for migration. Then there is the problem of format obsolescence. We saw as DNA solve the problem of media obsolescence, which means we will always be able to retrieve the binary information. But how can we show that this information will make sense in the future database? Therefore, more work is required to understand the applicability of open source binary file format. Moreover, new synthesis techniques are emerging. They dramatically reduce the cost to physically manufacture DNA, but also they are highly error prone. It's important to understand how to adapt consensus and clustering to the new synthesis techniques. Finally, state-of-the-art work on DNA storage has focused on using an object interface to DNA storage, which has several limitations. For example, the storage of small objects will occur in high overhead. Can we extend DNA storage with higher level abstraction like a file system to enable searching and indexing? In ongoing work, we are extending oligoarchive DSM to provide a block-based access interface to data stored in DNA. Thank you.